So I been messing around with this a bit here. So right now I've got that's implemented. That is not. Okay, this is not. This is. The user shader does work, but with some caveats. I need to polish it a little bit. Plan right now is to kind of oh shit, that's not hooked up. Yeah, anyway, so it's not perfect. I need to work on a couple things. The jittering is not correct, and I need to come up with an easy template for, like something to populate this with this to start, because this needs to be in there. The textures that are being accessed, and then I want to just have like some boilerplate logic for like testing against distance fields, kind of. Anyway, this is kind of like just a shape that I had a assign distance field for. There's something wrong with the directional light. I need to debug that. But anyway, so get some light on this thing and take a look at some stuff here. So today's adventure has been adding thin lens depth of field, which uses the jitter amount and a focus plane, like a distance to a focus plane, to create a real depth of field effect, which it's not fake through post-processing. It's actually jittering the rays to create a depth of field. It's not a full lens simulation, but it is the thin. If you look up the thin lens approximation, that's what it's doing. Takes a little while a couple of frames to converge, because those rays are being jittered like that. And it does add some to the render time. If you look at the timing while it runs, it's basically having to recalculate all of the rays twice. And the reason for that is this is the original calculation for the ray origin, ray direction stuff. And then there's a bool that gets passed in that's this. And then there's also a focus distance. Basically, the way it works is I calculate so this jitters the position, so it converges over time. One of the things that this does is it calculates all of the things as if there were no jitter, and the pixel goes through the middle of each pixel, right? Then figure out a focus point based on taking that unjittered ray origin and the unjittered ray direction and this focus distance, and then I get a new ray direction based on that, the offset from the jittered position, starting position, going towards the focus point. And then here we do the intersection that toggles between using that new value or the old value, and the same for tracing through the volume. So relatively simple, but pretty good results. Because you can scoot this in or out, and the larger the jitter, the thinner the depth of field. So, and also the noisier it is, it kind of goes hand in hand. But that's yeah, this isn't the greatest model. I like getting a little bored of it, but the tree model, I've made another one that's like not quite as boring. Yeah, clear the lighting, fix this. So we've got this model here, and this is doing the same thing to jitter the ray positions and everything. And yeah, when you move this focus distance in or out, you're moving where that focus plane is. So that's how that works. And it does get relatively expensive in terms of computation time. Yeah, so this affects the scale of the effect, and then this affects yeah, where it focuses in on, kind of like. Let's see, what else? Post-processing, yeah, so one of the big things I'm working on now, this is going to be the next thing, is the dithering. So I want to, as a post-process, I want to be able to dither either Bayer pattern, blah blah. There's going to be some settings in here, because right now it's just got color temperature, warm to cool, and gamma correction. So that's all that does right now. But then, yeah, the various tone mapping curves. There's several different ones. But yeah, so the idea then is that yeah, you'd be able to take this color result and quantize that in a couple different ways, similar to what I did in my SDF project, my little SDF testbed thing. And kind of, so in addition to the quantizing based dithering, I want to mess with palette based dithering. So instead of just reducing the precision of the existing colors, I want to also mess with an input set of colors that then yeah, basically doing some kind of distance metric on every pixel in the input image and finding the closest color, depending on, you know, and I want to try that in different color spaces, things like that, to try and you know, see if we can get some cool results out of that. That'll be mostly for aesthetic purposes. I also, this is another one that we're going to be looking at doing, is the what do you call it? The voxel jitter, or not jitter, dither. So to be able to take the data and have something like, I don't know, like either a blue noise pattern, just kind of figure out how I want to offset it for the layers, and then I want to come up with a 3D generalization of the Bayer matrix, which I think is doable. I haven't looked at it yet, but I think it's doable. I found a publication about three-dimensional dither patterns at one point, but I can't find it for the life of me now, so that's not very helpful. Anyway, the idea there is to reduce the color count. Like here, I've just done a blur on these things, and that means that I've created a lot of gradients of color here. So this is not just you know, 4 colors like it was before. Now there's a whole range of colors where these things intermixed at, you know, these boundaries and things. And yeah, so the idea is kind of like I'm coming up with a couple of different ways to quantize these colors and kind of reduce the color count, because when you go to save, PNG especially deals with high color counts poorly. So if there are a lot of colors versus not very many colors in a given model, then it's gonna have an effect on the file size. That's really just for these models that are the load save results. So anyway, kind of mess around with a couple different things. At some point I want to try and get linear interpolation working for the renderer. I think at this point it's kind of looking like I'm going to have to implement it myself, because I can't get the texture interface working, and I can't figure out for the life of me what piece of that is not correct. So that's going to be a matter of either figuring that out or finding another solution. But yeah, so anyway, that's kind of latest and greatest. I'm really very pleased with the depth of field. I'm able to do a real depth of field in a real-time application like this, just by jittering the ray origins and accumulating over a couple of frames. There is some ghosting, but I mean, you know, that's going to happen. But yeah, anyway, cool beans. Oh, and another thing here. So this is right. So another part that I've gotten working is the letters. So having yeah, we'll just pick some values here, and then yeah. So this is the font glyphs from Bitfont Core being applied here, just as like stamps into the space. And I think this is pretty cool. I think it really looks interesting with the depth of field calculations. Looks really spooky. Yeah, if you turn that effect down a little bit, you can kind of get a better sense of what we're looking at. Then related to that, pretty closely, let's go ahead and set the constant color here. The spaceship generator. So what this is it's a series of operations that, let's fix this. Series of operations that take those font glyphs and flip them, invert them, you know, stamp them into the volume, then copy them, mirror them, these types of things, to create a symmetrical, sort of symmetrical. It's hard to describe, it's easier to show. But yeah, they, like, it creates these, like, these types of objects that are like some font glyphs that got stamped into the volume and then, you know, flipped and mirrored based on some number of operations. The operations are like flip, mirror, trim, so there's just like chop off some amount of it, then stamping letters and these types of things. So you give it a random palette and, you know, it randomly generates these things with each letter picking from the palette at at runtime kind of. So then that gets loaded into the it's called the load buffer, and that's so that I can load it from the CPU onto the GPU and still respect the state of the mask inside the volume. So yeah, if you turn this up too much, it will kind of take much longer, because the main reason is that there becomes more and more voxels. It's held as a hash map of voxels. So 11 operations is maybe too much. But yeah, so it has to, because the way the hash map works, like, it has to create a new one after each operation, because there is some corruption that happens if you don't. So anyway, this one created this monstrosity. Go ahead and turn the jitter amount down. Let's be able to look at it. So yeah, you'd see how it kind of mirrored these things over and over and over and over again. So yeah, 11 is too many, but you can kind of see like the types of structures it makes. Now, what's cool is the thin lens stuff still works with the bizarre camera projections. So if I do the inverse projection and everything, it still is able to do all the same stuff as before. So, you know, kind of neat. What else? Yeah, this part is working, so I can generate the voxel automata terrain stuff. Oh, interesting. I had masked some stuff earlier. But yeah, you know, being able to adjust where that focus plane is and create some interesting looks to this. I want to, yeah, like I say, the interpolation right now is not a thing. It's just seeing cubes, and that's based on the fact that I'm using image reference for sampling. What else? Yeah, so the limiter compressor, this is going to basically be, for each channel, there's two different modes. There's a clamp mode and a narrowing mode. So what the idea is there is similar to the goal with the dithering. You take the data in the block and reduce the range by either narrowing 0 to 255 to the range specified, some specified minimum, specified maximum, and then you've got a much smaller range of values. It's still quantized to 255 values per channel because it's 8-bit, but I think that might still have some interesting potential. The other one, clamping, is literally just if the value is above your new specified minimum and below the new specified maximum, it keeps its value, otherwise it gets clamped to the nearest one of those. So, you know, yeah, the directional light has some sort of issue right now that's having to turn the decay up way too high, I think, which is making it go through opaque objects. But yeah, we're working on that. The cone lights are very cool. So if I clear this out to something lower, the way it's working now is it's 2 points specified. So I have the target point is set as the middle, and the position we're putting it here, if you look on the trident, it's back corner. So we set the width of the cone, that's in radians. Actually, I think it's not correct, it should be about half this value because, well, anyway, that's, yeah, so these are kind of a little bit arbitrary. So the distance power is, for the inverse square law, the 1 over the distance squared. That's where that's coming from. Instead of being squared, you can raise it to different powers. Yeah, so this is a light source that's very similar to the directional light, but it has some divergence because it comes from a point. And you specify it from some certain angle, so you're able to you know, do things like this. Anyway, yeah, so you get the light rays through the volume and stuff. I think this is all looking pretty spicy with the depth of field. That's really really works for it. You'll notice if I turn this way up, you do see some noise patterns, and that comes from the fact that I'm using a blue noise jitter. And so there will be some artifacts there. But yeah, so that's pretty much the size of that one.